Hi, this is Professor David Farina. In today's lecture, we're going to be talking all about the Earth and its moon, specifically Earth's geology, the interior, and the seismology that allows us to understand it. Let's get started. First off, Earth's interior. How do we know about it? There are actually ways to discuss and understand the Earth that don't rely on direct observation. What I mean by this is we can use information in the form of seismic waves, earthquake waves, to help us to understand what's going on beneath the surface. There are two main types of seismic wave. The first type of seismic wave is called a primary or P wave. These waves are pressure waves, and they move kind of like this, where they're compressing and rarefacting or stretching the rock itself. And so as a P wave travels through the Earth, its particles vibrate back and forth like so. The second type of wave is called a shear wave. And a shear wave moves kind of like this through the Earth, where the particles are vibrating up and down. Now, these two wave types act differently as they travel through the Earth. An earthquake produces both of these types of wave. Now, pressure waves, or P waves, will travel through both liquids and solids. So that's the first piece of information. It's very important. So pressure waves, the P waves, travel through both liquids and solids. Shear waves, on the other hand, will only travel through a solid. They will not travel through a liquid. Now, wave speeds are going to also be something that we can measure. And if we have a known distance and we have a time interval from when our seismic stations throughout the world receive a earthquake wave, we can use distance over time to determine speed. And speed is a direct indication of density. So the higher the density of the rock, the faster the waves move. Now, what is a seismograph? A seismograph is basically an instrument that measures the earthquake waves being produced. And as the earthquake occurs, it does take time to travel through the Earth. And so for this particular earthquake, it says earthquake occurs in Mexico, and a seismic station somewhere else in the world, it takes time for the waves to travel through the Earth and be received by the seismic station. Now, a P wave has a very distinct signature in a seismograph, and it looks something like this here. So the first P waves arrive first, primary P waves. S secondary waves travel slower, and therefore they arrive second. And you'll notice their amplitude is a lot higher here. S waves are, by the way, the more damaging of the two wave types, but we're not going to get into detail on that today. Now, why are we using seismic waves? Why don't we just drill into the Earth? The reality is that there's never been a hugely successful deep drill. When we get down deep enough into the Earth, the temperatures that we reach start to get high enough that the rock starts to move on us as we're drilling it. The drill bits themselves get very hot. And so as a result, we can't get even close to drilling down in towards the core of the Earth. We've merely scratched the surface of the Earth in terms of our ability to drill down. So we need to rely on seismographs and seismic waves to understand what's going on inside. Now, as I said, the P waves can travel through both liquids and solids. And so you can see in this graphic that the P waves are occurring, and here's the earthquake's starting point, the focus or epicenter of the earthquake, where it's being produced. And the P waves travel through the Earth, and they can go straight through all of the layers of the Earth. And so we end up with P waves here. We end up with P and S waves here. Now, we do also get this area where there's no P or S waves, and this has to do with the fact that the waves are going to be refracted or bent as the waves move through the different layers, and therefore the different densities of the Earth's in various layers. And so we end up with it's called a PNS shadow zone, and this is an area where no P or S waves are found. And by studying this and looking at many earthquakes over many years, scientists are able to reconstruct what the inside of the Earth must look like with great detail, both in terms of density and the location of the boundaries where these different densities and states of matter are going to occur. Notice at the bottom here we don't have any S waves at all. This has to do with the fact that the outer core of the Earth, indicated here by this orange layer, is a liquid, and secondary waves, once again, do not travel through a liquid. And so this is a really important discovery, and it helps us to understand what's going on inside. So, let's take a little deeper look at this. No pun intended. So as we look at the temperatures that the rock would melt at a given pressure and temperature, we can see that there is a graph here where we've got temperature on the y-axis, we've got depth with the x-axis, and as we look at these two plots here, we've got temperature being below the melting point, we have a solid. We have a crossing over point right about here where the temperature now reaches a temperature equivalent to the melting point of the rock at a given pressure. And so we end up with a liquid core. And you'll notice it's a very fine balance here. It's just barely enough temperature to melt that outer core. And then we have a crossing over point back here again, where now the melting point is once again going to be higher than the temperature itself because of higher pressures. Okay, so why does the melting point change? The melting point changes and gets to be a higher value as pressure increases as we go deeper. Temperature and its graph are going to also generally get higher, but may not achieve the necessary point to melt the rock. And so we end up with a solid core. All right, so this is the basic structure of the Earth's interior, and we'll get into the moon later on with this same graphic. We've got the inner core being about 1,300 or so kilometers thick, or in radius, I should say. That's the inner core, it's solid. We've got the outer core from the central region here is about 3,500 kilometers in radius. And then the mantle up to about 6,400 kilometers in radius. And then we've got the crust itself being anywhere between 5 and 50 kilometers thick. And this all depends on where on Earth you are. Are you near a mountain? Are you at the bottom of the ocean, near a trench where the layers are very thin? So this is the basic structure of the Earth's interior. Now once again, these PNS shadow zones allow us to determine this, and we're using seismographs, seismometers to study this interior structure. So this is the currently accepted model. The mantle is much less dense than the core itself. The mantle is rocky. The core is metallic, consisting mostly of nickel and iron. The outer core is also nickel and iron, but it's liquid. And volcanic lavas come from the mantle, allowing us to understand the composition of it. So we look at density, we look at temperature, we look at what the Earth is kind of spewing out in terms of volcanic activity, and we can really get a good understanding of what's going on inside. There's the basic structure once again. So thanks for watching the Earth and its moon, Earth's interior and seismology. I hope this was helpful in your understanding of how we understand what's going on inside the Earth. If you like this video, please hit that subscribe button, like the video, and if you'd like to get a notification each time I make one of these, please click that bell at the bottom. Thanks again. Hope you have a great rest of your day.